Yeah, thank you for the invitation. It's the first time that I give a seminar here. I'm very happy to meet you all, at least virtually. And actually, I really love to see that it's possible to go back to the university. That gives me hope that I will be able to do the same soon. So that's super nice. Okay, so yeah, the plan is to give you some sort of overview of the Swampland program. I was asked to give a review of the state of the art, focusing on what is known versus postulated, which was an interesting request. And I completely agree that it's very important to understand what is the, like, I can understand that it can be a bit confusing, and with all this activity going in the Swampland program, it's very easy to get lost and not being able to disentangle what is known versus what is postulated, and what are the serious and rigorous works that have been done finding evidence for the conjectures versus the works that just try to connect the conjectures, or that's, I mean, what are the things that we expect. So I think it's a nice request, and I will try to do my best to disentangle all this mess that I understand can be a bit confusing. And if you have any question, just please interrupt me at any point. Okay. Okay, so I'm gonna start very basic, so that we can be all on the same page. So let me just start with a very broad introduction by saying that I guess you all agree with me that effective field theories have been very useful so far in physics. Like, they give a description up to some energy scale, some cutoff, and this allows us to describe, for example, atomic physics without worrying too much about quarks and gluons and so on. And if we are interested in the description at a higher energy scale or smaller distances, then we need to UV complete that effective field theory so that it's valid up to a higher cutoff. Now, the question that we try to answer with the Swampland program is whether this is always possible. Okay, and in particular, we are interested in the case in which we try to UV complete that effective field theory in a quantum gravity theory at higher energies. And the answer that the Swampland program gives is that this is not always possible. Okay, that you cannot always UV complete some effective field theory that was anomaly free and was constructed using the rules of quantum field theory into a theory of quantum gravity at higher energies. Okay, so this is the main message. Like, not every effective field theory can arise as the low energy limit of a consistent theory of quantum gravity, for example, string theory. And the ones that can arise as low energy limits are said to belong to the landscape, while the ones that look apparently consistent, in the sense that they are anomaly free and so on, but still do not admit a UV completion in quantum gravity, we say that they belong to the Swampland. Okay? And the goal of the Swampland program is try to make this precise, like try to understand what are exactly the constraints that an effective field theory has to satisfy to be consistent with quantum gravity. So what distinguishes this landscape from the Swampland? And I mean, I think this is an interesting question by itself in quantum gravity, but the reason of, I think, or one of the reasons for the increased inactivity in the past few years is because we have realized that they might have phenomenological implications that are more important than what one could naively think at the beginning. So that not only that you need to satisfy some constraints, but also that these constraints are not negligible, that they have really non-trivial implications. And if this is true, I mean, if the quantum gravity imprint at low energies is non-negligible, I think this is great news for phenomenology, because it means that we can use these constraints as new guiding principles to progress in physics, like to construct beyond standard model proposals, and they can also bring new insights to solve the naturalness issues that we observe. Okay, so it could be that, I mean, it happens that these constraints are breaking with the typical, the expectation of the scale separation that is given by a Wilsonian effective field theory approach. And this could be behind the naturalness issues that we observe, so that quantum gravity might matter in the end. Okay, so this is sort of the idea. Of course, it's a very ambitious goal. I mean, we're trying to understand what are the constraints of quantum gravity. And for this reason, I mean, in the end, I mean, right now, all we have are proposals, okay? So there are many ways to approach these questions. I'm going to focus in this talk on what are called the Swampland Conjectures, which are a set of proposals that have been motivated by string theory and black hole physics. Now, I want to remark here that, yeah, I'm going to be assuming most of the time that the quantum gravity completion is going to be string theory, because in practice, I mean, even if this in principle is more general, in practice, I want to be able to test these conjectures in a consistent framework of quantum gravity, and string theory is a perfect playground to do so. Okay, so many of these conjectures, I mean, most of the evidence I will show you will come from string theory. Okay. So this is the map of Swampland conjectures that are more important right now and that I will explain in the talk. You can think that this is going to be my outline, in the sense that the goal will be to navigate this web of conjectures with you, explaining what they are and what is the evidence and the recent developments that have appeared in this respect. So I will not spend a lot of time with, I mean, I will try to be brief in each conjecture, but let's see, I mean, depending on the questions and everything, let's see if we are able to finish everything or not. So the first thing I want to remark is that, as you can see here, there are some lines connecting the conjectures. So I guess that one of the most confusing things for someone that doesn't work on this field is precisely to keep track of what the conjectures are, because probably it gives the impression that there are more conjectures appearing every year, and it might look a bit random. But what I want to remark is that I think one of the most, well, at least for me, one of the most important developments recently is that we are discovering that all these conjectures are not independent. So that they are not independent statements, but that they might be just different phases hinting the same underlying quantum gravity principles that we are starting to discover. And the goal here is precisely like to understand these relations, to try to reduce all these conjectures to the minimal set of statements that could reproduce everything. Okay, so even if it seems that there are more conjectures appearing, actually the number of independent statements is decreasing with the years.
So what is the meaning of the dashed lines?
So the meaning of the dot lines are the relations that I will explain. So whenever there is a dot line, there is a relation between the conjectures, which could be that one is a generalization of another or follows from another. So depending which one, it has a different meaning, actually. So I hope that will be, I mean, we will go through it slowly, and I hope it will get clear in each case what it means.
So Irene, if A is related to B and B is related to C, that means that A is related to C in these diagrams? Or?
It depends exactly on what the relation means, because sometimes it could be that, I mean, sometimes yes, but sometimes it could also be that it's a relation that appears in a specific context. So it's not clear that you can relate the two different contexts. So
I see. Very good. Very good.
It will depend. Yeah. The hope, I mean, I would say the hope is yes, but it's not, I mean, it's not at the moment, the relation that we have is not obvious.
So just, I noticed no de Sitter asymptotically. Are you going to speak even briefly on how you might reconcile that with the current observations?
Yeah, I mean, sure, I put asymptotically for a reason. which will be clear, which is that it doesn't forbid the sitter everywhere in the moduli space. So there are many ways to make it consistent, of course. I mean, it could even be consistent that we live in a quintessence era, but I put the word asymptotically to show, I mean, I will explain, but we'll see it. I'm going to focus on what is the evidence that we have and precisely what are the statements that are supported and not just conjecture. And I think the evidence that we have for the absence of the sitter comes from the asymptotic regions of the field space. So that's what I will explain. Okay, any other question? Okay, so let me put a bit of order here. First of all, the first ones here on top, they sort of constrain the kinematics of the effective field theory, while the others constrain the dynamics. In particular, the ones in the middle constrain the field spectra. Okay, so they tell you they predict the existence of new states, while the most recent, the last ones that I have on the bottom, they constrain the scalar potential and the landscape of vacua in quantum gravity. Okay.
What do you mean when you say it constrains the kinematics?
It means that, yeah, that is not, that it doesn't constrain anything about the dynamics in the sense of the interactions or the masses or things like that. So it's going to be all about like exact global symmetries, which means that doesn't tell you at what energy scale you should be sensitive to that particular feature. While the other ones will constrain the interactions and the masses, the potential, and so on. So they are correlated to some energy scale, some dynamics. Okay. Any other question? Okay, this is from the perspective of the effective field theory, not from the quantum gravity. Okay, there everything could get mixed. Okay, so let me start with the principal one, which is the absence of global symmetries, from which we will see that many others follow. Okay. So the first statement is that there are no global symmetries in quantum gravity, meaning that any global symmetry should be gauge, so should be associated to some gauge degrees of freedom, or should be broken at some energy scale. Originally, the motivation from this comes from black hole physics in order to avoid to end up with some infinite number of remnants, because Hawking evaporation is blind to the global charge, so there's no way to distinguish different black holes with different global charge, and this could violate entropy bounds. But the reason why this conjecture is the most, I would say, widely accepted one in the community is because the evidence that we have gathered for it in the past years. So as a summary, well, first, of course, there is no counterexample in string theory so far of this, but also already in the Polchinski book, we know that there are no global symmetries in perturbative string theory. Okay, so that any global symmetry in the Warshik CFT, it's gates in the target space. And a similar result have appeared more recently by Harlow and Oguri for the case of splittable symmetries in ADS-CFT. So that they also show that a global symmetry in the bulk would be inconsistent with locality of the CFT.
Irene, can you comment on which of these pieces of evidence also apply to discrete symmetries?
Yes. So the proof of Harlow and Oguri applies for discrete symmetries as well. It's not just continuous. And actually, yeah, the one of Polchinski is about whether you have a current. So that's what matters. The arguments of the black holes, it's only for continuous global symmetries, but that's, I would take that as a heuristic motivation, not as a real proof. So then it seems that, at least from the arguments of ADS-CFT and so on, it seems there is no difference between discrete or continuous. That doesn't really matter.
But I mean, isn't it true that for global finite symmetry groups in de Sitter or flat space, there's no argument against them?
For global finite symmetry groups? What do you
In
have in mind?
asymptotically flat or asymptotically.
Okay,
conformal
yeah.
space.
You mean like,
Like,
but that's,
like more or less the real world.
I don't know if you are talking about like all these soft theorems and like large case transformations or things like that.
No, just
Or
a
just
finite
change the
symmetry
background.
group. Just a finite symmetry group, like some, pick your favorite finite symmetry group. M24, L2 of 7, the
The
tetrahedral.
idea
group.
here is that, the point here is that, so any of these symmetry groups, if they act non-trivially on the Hilbert space, okay, and they are not gates, in the sense they are not associated to some gauge degree of freedom, they should be broken at some high energy scale. Maybe from the point of view of the effective field theory, you could still have some global symmetry, right? Like you could still, in the infrared, you can use these approximate global symmetries to order, to construct your Lagrangian, but they should be broken at some very high energy scale. So there should be some non-renormalizable operator that is breaking that symmetry.
But why? I mean, that's a scenario, but do any of these arguments actually rule out this possibility?
So Jeff, I think if you look at Zn, say for very large n, you might run into some entropic problems again in the basic black hole arguments.
Okay, but what about just A5 or just
something small? I don't have any idea, but for a large order finite group, you might have to say something weird about black holes. Yeah.
Okay.
I think the modern understanding is that quantum gravity, quantum gravity should allow for topology change. Like topology is not going to be an invariant of quantum gravity anymore. And what's probably happens is that any symmetry that is associated to some topological operator should not be allowed in quantum gravity, because that's not an invariant. There should not be topological operators or topologically conserved things. So I agree that the black hole arguments only works for this continuous group, or if you take the n very large, but I think we are starting, we should start changing probably that perspective, because I agree it's not completely complete. And I think it's going to be more related to this topology change, which also connects with this third piece of evidence that people have connected the absence of global symmetries to unitary black hole evaporation. So all these recent developments about reproducing the page curve and so on are also useful to show the absence of global symmetries, because all these replica wormholes and all these tricks that they use are breaking the global symmetries. And more generally, it seems that if you allow your path integral to sum over different topologies and processes that change the topology, this is going to break the global symmetries of the EFT. Of course, we have to make this much more concrete, but that would be the message underlined. Okay, so so on one hand, I agree, we need to prove it in a consistent framework like string theory and ADS-CFT, but it would be nice also to understand why, like from a bottom-up perspective, why this is not possible and how to connect it with this topology change. Also, I want to remark that the notion of symmetry itself is changing, right? Like the recent years, there is also a lot of activity also from people here in the audience studying generalized global symmetries and many structures that are derived from this. And the question is to what extent all these generalized global symmetries are forbidden in quantum gravity. So the goal that comes when you study this in the Swampland context is that you try to understand what are the specific mechanisms for which quantum gravity should avoid all these symmetries. Because I think, what we are seeing is that not only we can learn a lot from the presence of symmetry in a theory, but also from the absence of them. Because there are many features that can be understood as consequences to avoid those symmetries. So I want to give you some examples about this. And for that, let me just probably review the most canonical example of generalized global symmetry, in which the basic thing, I think, is that we use a language in which, instead of talking about global symmetries that commute with the Hamiltonian or the stress energy tensor, these symmetries are characterized by some topological operator, okay, by some operator which has to be topological. That's the sort of the equivalent thing. And this generalized notion comes from the fact that we allow the global charges to be carried by higher dimensional objects. Okay, so the charge operators of a p-form global symmetry are going to be supported on a p-dimensional manifold. And the canonical example for this is, for example, if you consider Maxwell theory, you have a one-form global symmetry with a current that is given by the electric or the magnetic field strength. And the charge operators are not local operators, they are these Wilson lines, okay, that they create sort of strings, no? One-dimensional states. So the charge is carried not by particles, but by these strings. And how this symmetry is broken is well known, that these one-form global symmetries get broken when you have charged particles in your theory. So that, for example, the conservation equation of the current is non-vanishing when you have charged states. And that means that these Wilson lines, these operators, can break. No? So they can break by inserting these local, the local operators associated to the particles. So in this example, you could say that the existence of charged particles could be a consequence of requiring that you don't have these one-form global symmetries in your theory. And the goal is try to understand to what extent these conditions are necessary or sufficient, like exactly what are the string theory features that you can interpret as necessary conditions to avoid generalized global symmetries. Okay, because more generally, if we consider other types of symmetry, it's not just going to be about having charged states, but there could be many other features that can be derived in this way. So just, again, to give one example, in this recent paper, we studied what we denoted as Cherbyte global symmetry, so that the currents are given by products of gauge field strength. So it's not just F, but also F with F and so on. And then the thing is that these symmetries in general are not easy to break because of the Bianchi identities. The conservation in the absence of charged state is guaranteed by the Bianchi identities. And then by analyzing how string theory gets rid of all these symmetries, we realize that typical string theory features, like top-down features as the existence of actions, Chern-Simon terms, localized degrees of freedom in the work volume of the monopoles, the process of brain dissolving on or ending on brains and so on, can be understood as consequences of avoiding all these Cherbyte global symmetries. Okay, so this is what I meant when I said that I think we can learn a lot, not just by the presence, but also from the absence of global symmetries in quantum gravity. Okay, so let me mention a bit the completeness hypothesis, which would be the next conjecture, which is that every charge of the gauge lattice consistent with Dirac quantization should be populated by a physical state in the theory. Okay, so that you need to have charge states, right? Like for all charges, you should have some state. And originally, the motivation also comes from black hole physics and so on. But the more modern understanding is that this might just follow from the absence of global symmetries. And I already gave you an example because I told you that when we have Maxwell theory, we have this one-form global symmetry that gets broken if you have charged states, if you have electrons. And the thing is that only if the spectrum is complete, then you can completely break the one-form global symmetry, because otherwise it will get broken to some subgroup. So if you want to avoid any global symmetry, you need to have a complete spectrum of the theory.
Does physical state mean single particle state?
No, it means, no, it can be a multi-particle state. So it means that you need to have like single particle states for the generators, right? So that's then you can generate the full lattice with multi-particle states. So like the unit charts are going to be single particle, but in general, it can be about multi-particle states. It can even be a black hole in principle.
Irene, is the existence of every charge equivalent to the existence of a minimal charge state?
If you need to have the minimal charge state populated?
No, I mean, just from the point of breaking, say, one-form global symmetry, you just need to have a minimal charge state so that all Wilson lines can be screened.
Well, you need to have, like, if you have just, if you just have one field, one gauge field, then yeah, you just need to have the minimal charge state, because then you can have multi-particle states, right? And like you are breaking everything. If you have several dimensions, like you have more gauge fields, you need to be able to populate the full lattice.
Okay, nice.
So it's like having, yeah, unit charge on each direction.
But you could also, if you have multiple fields, you could also have multiple fields with coprime charges and have the charge one thing be multi-particle. That's why I asked the question.
Yeah, exactly. Yes. Yeah, so you need to be able to populate everything.
How can you actually tell what a physical state is in the low energy theory without some ultraviolet data?
That's why, so yeah, right now, that's why I was saying like this is sort of about the kinematics. This is not putting any constraint about what is the mass of the states or when the global symmetry should be broken, right? So it could happen at a very high energy scale. So it seems it's not constraining the infrared in that sense, okay? I think it could still be that, as I said, like sometimes when you consider more general symmetries, it also gives information not about just the states, but how they should interact with each other to break and gauge everything in a consistent way. So if I just have one gauge field, it doesn't give any implication for the IR because the mass could be very large and who knows. But in the moment in which you start having many pieces together, it's not so easy to gauge and break everything in a consistent way because they are kind of interconnected. And then you can have constraints. And what I mean, in a couple of slides, I will finish this like sort of global symmetries completeness hypothesis, and then we will go to the other conjectures, which precisely try to quantify how much you have to break these symmetries and what will be the masses of these states. And then those really have implications for the infrared. Okay, so what I said here, it's a bit cheating in the sense that this works. I mean, this relation between the complete spectrum and the absence of global symmetries, it works very nicely for a continuous gauge group. But there were actually some counterexamples for finite discrete groups and disconnected groups. And recently we were studying this question in detail, and we show that at least for isolated groups, one can show that there is a one-to-one correspondence between a complete spectrum and a more general notion of global symmetries, which involve non-invertible global symmetries, in the sense that if the spectrum is incomplete, maybe you don't have a global symmetry in the usual sense, but you still have some topological operator, which doesn't satisfy a group law, but has a more complicated fusion law, and in particular, the operator doesn't need to have an inverse. That's why they are called non-invertible global symmetries. And yeah, this is like the analysis of these non-invertible global symmetries is also important in other areas of research, and it's I think a fascinating topic. But maybe all I want to remark is that I think this is hinting that probably what is wrong in quantum gravity is to have some topological operator at all, right? Like, as I was saying, that topology is not something that is invariant, can change, and there shouldn't be topological operators in quantum gravity. And that statement is what maps exactly with having a complete spectrum. Okay, so following this line of reasoning, that we want to allow for topology change in our theory and so on, there is this other conjecture about the triviality of the Bordesine group, in which one tries to phrase this in a more mathematical way, I would say. So the idea, the conjecture is that the co-Bordesine group of a quantum gravity theory should be trivial, precisely to avoid some p-form global symmetry with charges characterized by the non-trivial co-Bordesine classes.
Can you say what you mean by the co-Bordesine group?
Yes, I'm gonna say. So what do I mean with co-Bordesine group? So co-Bordesine group, I mean, might sound a bit exotic if someone haven't heard about it, but I think the intuition is very simple. It's just that it's an equivalence relation in the sense that if you have two manifolds of the same dimension, these two manifolds are going to belong to the same class in this co-Bordesine group, are going to be bordant to each other if their union can be understood as the boundary of a manifold of one dimension more. Okay, so it's about classifying what spaces, what manifolds can be boundaries of other ones. And the thing is that this equivalence relation has an abelian group structure and has a trivial element, which is the case in which a manifold is a boundary by itself. Okay, so that it can be the boundary of another manifold of one dimension more. So in particular, you can shrink it to a point. Okay, so the idea is that if you have your quantum gravity theory, like string theory, in higher dimensions, like in dimension D, and you compactify that theory in one of these manifolds, you are going to get some effective field theory in the infrared, right, of dimension D minus, well, this D should be K here, sorry, this would be the same letter. So you have some effective field theory where these are the internal dimensions, the compactified space. And the existence of this cobordism, so the possibility of joining, that the union is at the boundary of another one, gets translated to having a domain wall between the two different effective field theories. And in the case of the trivial class, it's like if you have some end of the world brane, so that there is nothing behind. So the idea is that if this cobordism group is non-trivial in the sense that you have different classes, it means that you cannot connect some effective field theory to another one. Like you cannot, there are different classes that cannot be connected to each other. And these different classes, they are topological global charges that distinguish that effective field theory. And there is no way to get rid of that charge. So there are some cases in which these global charges correspond to usual symmetries in the theory. Like, for example, all these P4 global symmetries in which the current is the gauge field strength and so on can be understood also as cobordism classes. But it also allows to have more general symmetries than the ones generated by gauge fields and so on.
Irene, sorry for interrupting you, but I'm still a bit confused. So in the notion that you explained of cobordism group is an existing mathematical structure, and it is not in general the trivial group. So what does it mean? Yeah. What is the cobordism group of a quantum gravity theory? What does it mean to talk about the quantum gravity theory there?
Yeah, so here, exactly. So the thing is that when you compute this cobordism group, so it matters the dimension of the manifold that you're considering, but also the structure. Like for example, you have some fermions and you have some spin structure, or if you have fluxes, or
Yes,
there are
yes,
many
yes,
more
yes.
things that you have to include. So
Yes.
when I put here quantum gravity, it means that you need to have enough defects in your theory to have a trivial covariation group. So that, for example, if you study this covariation group when you have fluxes, then you would get that it's non-zero. But if you add branes, now these branes trivialize the covariation group. So it's telling you that a quantum gravity theory with fluxes but not with branes is not consistent. So you need to have a source for all this extra structure that you have. So yeah, so it's so the way to understand this is that
a precisely defined group, or is this just an idea for a group?
No, I don't think it's not a. I mean, in practice, in examples, of course, it's a precise thing that you can check. But when they claim like the quantum gravity covariation group should be trivial, it's not well defined because you don't know what are the possible structures that you can put in a quantum gravity theory yet, right? Like you should be able to classify all possible structures and then.
By structure, what do you mean by structure?
I mean, yeah, like exactly, like spin structure, fluxes, like all the possible things that you can add here, right? That would be the subscript, like the of this code.
You know, when one studies anomalies or things like that, where in other contexts where cobordism groups come up, you usually decorate your manifold with a spin structure if you're talking about fermions, or U1 connection if you're talking about theories with U1 global symmetry. So what are you talking about structure beyond that? What do you mean by saying we include the defects in the definition of the cobordism group?
Yeah, I mean that structure and the defects that trivialize that structure. So for example, if you have a spin structure, you can have a spin defect. You have some fluxes, some spin C, you can have the branes, and this trivializes the group. That's extra information. I mean, like the defects that you have in your theory are part.
Can you draw a picture or explain how a defect trivializes the group? I just don't quite get it yet.
It's because, so think for example, like, so the case of the, if you have some manifold, with some sphere with some flux, in general, you cannot shrink. I mean, to be in the trivial class, it means that you can shrink that manifold to a point.
Yes.
So if you have some flux, that's a topological obstruction to do that because of conservation of the flux, of the charge, right?
Yes.
Now, if you have some brane, for example, that acts as a source for the flux, you are able to do that. You can shrink it to a point because it could be that the total charge is conserved because you have some flux, but this is compensated by, you can cancel that Pauli conditions and so on, so that is compensated with the charge of the brane itself. So that the total charge is zero, and therefore the cobordism group for that manifold is zero.
I see.
So it's like whatever you need to add in order to be able to shrink that manifold to a point, and to get rid of the extra thing that you are adding, like fluxes or other things. Sometimes it's not necessarily to have a defect as we think of a defect, like a brane, for example. It could be that you have a Chern-Simon term. For example, I can have some sphere with some flux, and it seems that it's not, like I cannot shrink it to a point. It seems that it's in a non-trivial class of the cobordism group. But if that gauge field appears in some Chern-Simon term, I can get rid of that flux because of that interaction. It's like you are gauging or breaking the corresponding P4 global symmetry associated to that gauge field. So whenever you are able to break it or gauge it, the cobordism group that you are going to compute is going to be zero. So it's equivalent, like that would be the point. Like if you have some conserved global charge, the cobordism group is going to be non-zero. If you are breaking all the global symmetries associated to all the fields and everything you have in your theory, including geometry and everything, then the cobordism group will be zero.
Okay, so it's a statement about the existence of branes carrying sufficiently rich charges, basically.
Yes, branes carrying charges or Chern-Simons terms, like
Well, the
love interactions?
Chern-Simons terms just break the symmetry to begin with, so that part seems a little more transparent. The ones that seem more interesting are the
Okay.
Yeah.
Yeah, okay. It depends what is the theory you start with. Yeah, how you define the original theory. But yeah. Yes, and precisely this has been used to predict the existence of new non-supersymmetric branes in the string theory. Because there are some cases in which the defects that trivialize the covariance group are usual D branes or NS5 branes or I don't know, like usual things. But in other cases, the defect that would trivialize that covariance group is not known in the string theory. And one can show that actually is breaking supersymmetry. So in these papers, Kumrun and collaborators, they use this to predict the existence of these new non-supersymmetry defects and then try to find them in the worksheet or like things like that, like try to understand what they are.
And was that successful? Did they find them from other means?
So yes and no. I mean, depends which one, how difficult it is to find. For example, like I didn't put it here, but you can also use these covariance groups in the moderate space to reproduce all the structure of PQ branes that you have in F theory, and which is beyond perturbative level. So it's something that it's a posteriori, I mean, it's something that was already known that you have all these PQ branes as well, but you can also already derive in this way. And it can also be used now for lower dimensions, in which is not so clear. Like when you have F theory on K3, it's clear what are the singularities and the structure of PQ branes, but in Galavilla 3, 4, and so on, the classifications are not always complete. So now you have two different ways to approach the same problem. And hopefully this will bring new results. Yeah.
Okay, thank you.
Yeah.
Sorry, Irene, can I also ask a quick question?
Yes, go.
So this is some constraint on the type of space-time topologies that are allowed in your quantum gravity theory, right?
No, I don't think.
It's not only, I mean.
Why is it a constraint on the type of space-time topology? The topology could be whatever you want. You just have to postulate some new brane to destroy it.
I mean, it depends. Okay, here you are making a very big distinction between the geometry and the branes. It could be that all this distinction is a bit artificial from a UV perspective, because sometimes you can, like for example, with the Chern-Simons terms, you have like some sort of charge dissolved everywhere, and you can then bring that to a localized object, or vice versa, right? Or you can have some brane dissolved in a brane, because you have the Chern-Simons interactions, the Chern-Simons terms of the work volume brane, and then you can push that instant charge away from the brane and get some localized object. So I mean, it's not, from an IR perspective, there is a clear difference, but from a UV perspective, I don't think the difference is so obvious always.
I agree with that. I was just reacting to the question saying, I don't think it's a constraint on the topology of the red space in the diagram.
I mean, if you're just, forget about most of your structures. If you just want to take like an orientable space-time, isn't that cobordism group just non-zero?
Right,
general?
but she's saying there exists an object in quantum gravity that can change the topology such that a neighborhood around it would create that would create that topology.
Yeah, exactly.
Okay. Okay, I'll think about
that. Yeah, that's the way, exactly. That's the way this conjecture is understood. You need to have enough defects to guarantee this. Which would mean that, yeah, from the EFT perspective, it would mean that any effective field theory can be connected to each other, because you always have some domain wall that allows you to interpolate between the different effective field theories.
So in particular, would it mean that any low energy EFT in quantum gravity coming from a consistent quantum gravity has a gapped boundary condition, has a boundary to the trivial theory, has a suitable boundary?
Yes, exactly. Yes, indeed. It has an end of the world brain. And this is, well, I'm not going very well in time, so I'm not sure if I will get there, but when studying the conjecture that any non-supersymmetric vacuum should decay, then there is a correlation. Now there is a new relation that appears to this conjecture, because this is telling you that there is no topological abstraction to have bubbles of nothing, like everything. You can always nucleate a bubble of nothing in your theory. Okay, so this would be like the more general. I don't know.
So can you comment? You did before, but can you comment on what is the evidence for this? That this idea, like concretely, why should we believe it?
So yeah, so the evidence. I mean, in many cases, this reduces to usual symmetries. So would be the evidence that we have for global
right,
symmetries.
But it is a generalization because.
But it's exactly. So it's a generalization. The generalization. I mean, in general, sorry. In some cases, you could still try to use the heuristic arguments of black holes, because you can always throw these manifolds to the black hole, and then there is like a global charge and so on. So it has the same type of motivation, but there is no, I don't think there is no independent evidence beyond the one we already have for usual symmetries or the heuristic motivation of black holes. It's just, yeah, it's a generalization that I mean have to be studied in more detail. It's just that, I don't know, like if you think that what is wrong is that, yeah, you cannot have topological invariance in this sense in quantum gravity, like you should allow for topology change and so on, then this coordination group should be trivial. Like everything should be connected to each other. But it's an argument, it's not an evidence. So that's all we have so far.
But I don't see concretely like what would be weird if this were false, but the other conjectures were true.
It would mean like some topological operators are fine and others are not. Like you allow some global symmetries, but not others. Just because some global symmetries you can understand them in terms of currents and gauge fields, and maybe others you cannot, but they are about the geometry and gravity, right? So maybe it's just that they have a more difficult. I mean, it could be just a technical thing. It's weird to think of a conceptual reason how to distinguish that, because it's just about different topological operators. It's just that some are made with gauge fields, others are made with gravity or geometry, and why one should be different from the other one. I know it's not a rigorous argument, it's just that there is no clear distinction, in my opinion, among the ones that we are more confident about than these ones. But it's something to explore, because also there are some cases in which they can be very exotic. For example, if this dimension is 0. And this is what relates to -1 for global symmetries and the absence of free parameters and so on. And those cases, yeah, it's not clear at all. It's a work in progress to understand a better evidence or a better motivation for them. Okay, any other questions? Should I go on? Okay, so this was it for exact global symmetries. What I wanted to discuss after this is what about approximate global symmetries? So can we quantify somehow how much we have to break these symmetries, or what are the scale, the energy scale, or the masses associated to the charge states that break the symmetries and so on. And the point is that, well, if we are able to do this, then we really have constraints on the IR effectivity theory. We can say how much we have to break them, at what energy scale we should be sensitive to the effects. And the thing is that the rest of the Swampland conjectures try to quantify this. Okay, they try somehow from different perspectives. They sort of quantify how close you can get to the situation of restoring one of these global symmetries. Okay, so let me just give you the intuition very quickly. So what I wanted to say is that, like, if you have your parameter space in your theory, if we assume now that global symmetries are not allowed in quantum gravity, you could ask, okay, what happens if I try to restore a global symmetry by moving in this parameter space? Like, for example, I can send a gauge coupling going to 0, and that will restore a U1 global symmetry. Now, this parameter space, from the point of view of string theory, is like the field space, no? Because parameters are typically parameterized by the vacuum expectation value of some scalar fields. And this is also related to the absence of free parameters and -1 for global symmetries and so on. And the point is that if global symmetries are not allowed in quantum gravity, what should happen and what happens in practice is that the points in which you would restore some global symmetry are at infinite distance in this field space. Okay, so they are pushed to the boundaries of the field space. And this is what we call the asymptotic limits, okay, which go near one of these boundaries. And the thing is that from the perspective of quantum field theory, the region, like before reaching to the boundary, like the region around, it should be completely fine. Like you get an effective field theory with a weakly coupled gauge field, or maybe some approximate global symmetry and so on. And this is good for quantum field theory because it's precisely the regions in which we have perturbative control and we know how to compute things. But according to quantum gravity and this no global symmetry conjecture, something should go wrong if you try to approach those boundaries. And so that if you are able to reach that limit in a continuous way, you should be able to see how the effective field theory is breaking down when you try to restore the symmetry. And what is behind all these conjectures is that all these phenomena in which you get close to restore some global symmetry by having a weakly coupled gauge theory or a large field range and other features on the potential, all these things come at a price. It's like you can have them, but at the same time, the cutoff of the effective field theory should go to 0 as you try to make the symmetry better and better. And this means that you should get new light physics, new states that are forcing this cutoff to go to 0. And this is what is behind the weak gravity and the distance conjecture. Okay, so they predict the existence of new states that will force this cutoff go to 0 and act as a quantum gravity obstruction to restore the global symmetry. Okay, so regarding the weak gravity conjecture, okay, let me ask, how long can I continue? Because maybe this way I can decide how much to spend on the different conjectures. Like, how strict are you with the time?
Not strict at all.
Not strict at all? Because I mean,
it's
started a little bit late too.
It's a remote seminar. People can just leave. You won't even
okay. Okay, then I will continue. And if at some point, like, you want me, okay, go a bit faster or something, like, just feel free, okay? It's completely up to you.
Sure, sounds good.
Okay, so the weak gravity conjecture. So the weak gravity conjecture, the conjecture says that given a gauge theory, there should be some electrically charged state with a charge to mass ratio bigger than the charge to mass ratio of an extremal black hole in that theory. I put here that this is equals 1. It's actually some order 1 factor that depends on the dimension of the space-time and, well, and the theory itself, okay? Now, here you can already see that the point, well, there is a magnetic version of this conjecture, which is that you apply this to the magnetic gauge field, and then this gets translated to a bound on the cutoff of the effective field theory. So that indeed, when you try to send a gauge coupling to 0, you are going to get light states. I mean, the charge is proportional to the gauge coupling, and the cutoff of the effective field theory should go down. Okay. Now, in principle, this should apply not just for particles, but for any p4 gauge field that you have. Okay, so if you have a 2-4 gauge field, then you are talking about having strings. And if you have an axion, then it means that you should have some instanton that is electrically charged under the axion, such that the mass, which is like the instanton axion, is smaller than 1/f. which is the decay constant. No, that would be the inverse gauge coupling. And this combined with the requirement of perturbative control is what gave to the statement that Transplanckian actions are disfavored in quantum gravity, which is what triggered all the activity on the Swampland program 5 years ago. Okay, because of the connection with inflation and so on. Now, what is the evidence that we have for this? No? So I collected here the evidence that we have for the weak gravity conjecture. Well, first, we have many examples in string theory, which we identify what are the states satisfying the weak gravity and so on. But also there are several people that have tried to find a proof or semi-proof of the weak gravity from different research areas. In particular, for example, we know that the weak gravity conjecture is connected, can be derived from modular invariance of the 2D CFT, so that if you have some gauge field that has a worst description, then you know that the weak gravity conjecture has to be true. And also in ADS3, CFT2, you can also use it to prove the weak gravity in ADS3. But it's not clear, it's not known what would be the higher dimensional analog of this yet. Okay. Also, there are many works like studying higher derivative corrections to the black holes and positivity bounds, right, from requiring unitarity and causality and things like this. And all these works, I think the lesson to learn is that it seems that, well, I think the lesson for everything is that it seems that a mild version of the weak gravity conjecture should be true. Like you should have some states that satisfies the weak gravity, but it's not clear at all which state, like whether it's just about black holes or whether you have light particles satisfying the weak gravity conjecture. Okay, so all these, yeah.
I was just going to ask. So in the original weak gravity paper, you mentioned there's a number there, not just one.
Yes.
That comes from the extremal black hole. So which of these evidences make reference to that number, or do they just all say that it can't be parametrically wrong?
Well, I would say most of them is not all. I would say even all is about that number. So because it's about extremality, right? Like that number is about, you are comparing the charge to mass ratio with the extremality bound of the black hole. So you need, in order to check the weak gravity, you need the two things. You need the information about the charge to mass ratio of the states in your theory, but you also need information about the extremality bound of the black holes. And in all these studies of unitarity and higher derivative corrections and so on, you use the information about the extremality bound of the black hole. So it's really about comparing with that number. And also the relation with the cosmic censorship conjecture and so on, it's also about that number. So I think the only one which was not obvious was this modular invariance of the 2D CFT, but in an ongoing paper that Ben is going to publish soon, here shows also that is associated to the extremality bound. So I would say that the main open question here is about, like what states satisfy this? Like it's enough to have small black holes such that the higher derivative corrections deviate from the extremality bound, so that the charge to mass ratio is bigger, or it's about light states, or what's going on? And this is like the $1 million question. So who must satisfy the gravity conjecture? Because this is essential, this is very important if you want to give any phenomenological implication, right? Because all the phenomenological implications are based on assuming that you have light states that are satisfying the weak gravity. Okay. So in this sense, there has been like different versions for the weak gravity trying to answer this question. And at the moment, the strong version that dominates is this sublattice or tower weak gravity that says that there is not only one state satisfying the weak gravity, but you have infinitely many. Like you have a sublattice or a tower of states satisfying the weak gravity conjecture. Okay. What is not clear, is that if we, for example, have a sublattice, what is the index of this sublattice? Okay, because even if you have a sublattice, it could be that, right, the first state, no, of the weak gravity satisfying particle could still be very large. So depends how sparse, no, is this lattice, the phenomenological implications will be stronger or not. Okay, and this is also very important for inflation. I mean, when you hear people saying that the weak gravity conjecture constrains inflation, it all depends on the assumption that the instantons that are satisfying the weak gravity are also the same instantons generating the inflationary potential, which means that they are like the light instantons. No? If they dominate the potential, it's because the action is smaller. So it's all about having this index of the sublattice small enough. Okay, what do we know about this? Well, why we think there is a sublattice or a tower and not just one particle is because, well, first, only a sublattice or a tower would be consistent under dimensional reduction. Like otherwise, it's a statement that could hold at some dimension, but then you dimensionally reduce and then you don't satisfy it anymore. So the only way in which this statement is like a quantum gravity constraint that doesn't care about what dimension of the space-time you are talking about is that you have more than one state and you have infinitely many. But more concretely, also like these works of modular invariance of the 2D CFT, they require to have a sublattice. It's not enough. I mean, you generate a sublattice, not just one. And then all the string theory examples, I mean, whenever we check the conjecture in string theory, it's true that you always find that you have a sublattice or a tower and so on. But this is just example based, okay? I can also say that, I mean, looking at examples, we've never been able to find some index of the sublattice, which is bigger than some other one. I think the biggest one is around 6 that we could ever find. So, but this is an open question. Like in examples, we always find that this index is very low, which means that indeed you have light states satisfying the weak gravity and the phenomenological implications apply, but there is no proof of how big can it be, of whether there is an upper bound. This is like an open question and would be very interesting to find it. Okay. So this is what I wanted to say about the weak gravity. This is the main open question. Let me tell you now a bit about the distance conjecture. Okay. So the distance conjecture claims that there is an infinite tower of states that become exponentially light at every infinite field distance limit of the modular space, meaning that an effective field theory can only be valid for a finite variation of the scalar fields. Because if you try to make this variation parametrically large, you are going to get an infinite tower of states that become light in terms of the geodesic distance between the 2 points. Okay, so if I am moving in this modular space, which is parameterized, no? This is scalar manifold, which is given by the nonlinear sigma model of my scalar fields, and I have a metric, no? Which is given by the field metric, the kinetic term of the scalars. If I start at some point Q and I move to another point P of this modular space, the conjecture tells you that you should get an infinite tower of states that decay exponentially in terms of the geodesic distance between the 2 points. And this is something which is very, I would say even normal if you work in string theory, because we are used to have, I mean, whenever we approach the boundaries of the field space, we always get tower of states that become light and that are pointing to a new weakly coupled description of the theory. So it's like trying to understand why the distance conjecture is true. It's like trying to understand why we have dualities in string theory. So that, for example, when you decompactify, right, you get all the KK tower, you know, the Kaluza-Klein tower of states becoming light. But also when you send the volume to 0, you are going to get winding modes that become light and they are related by duality and so on. And the thing is that this is the simple example, but it seems that this is true for any direction of the modular space that you could have, which is much more complicated than just decompactifying. So in lower dimensions, you get many different distance, infinite distance limits, and every time you get some infinite tower of states. hinting some duality. Okay. So here from a phenomenological perspective, let me say that this infinite tower of states implies that the effective field theory is breaking down because we cannot have infinitely many fields weakly coupled to Einstein gravity. Okay, so this is always about having some effective field theory weakly coupled to Einstein gravity. And this in practice implies an upper bound on the field range. Okay. Now, in order to be precise, the main, as I said, the $1 million question here in the conjecture is to determine what is this alpha, what is the exponential rate of the tower. Okay, so how fast it becomes light. And this is essential before concluding, I mean, whether Transplanckian field ranges are ruled out or not, no? Because it all depends on this number. So in this sense, the evidence that we have for this, it just comes from string theory. So this is different to the weak gravity. In the weak gravity, like there were different approaches, no? Like people working also on black hole physics and other things. Here, the distance conjecture is very linked to string theory examples. So in a sense, it seems like kind of unavoidable if you work in string theory, but we are kind of we miss what is the bottom-up rationale for the conjecture, like why this should happen, okay? And there are some proposals for this based on the emergence proposal, so that the infinite distance itself emerges from integrating out the infinite tower of states. And also, as I said, the obstruction to the global symmetry, because in practice, in the examples where we see that there is a global symmetry that would be restored at infinite distance. But it's kind of an open question of research to have a better motivation for this conjecture from a bottom-up perspective. Okay. Now, let me give you what is the more concrete, what is the evidence? I mean, when we have checked this conjecture, because here this is a topic in which there has been a lot of research in the past few years. And I just want to summarize in what setups we have proven that the conjecture is correct, and we have computed what this alpha is. Okay. So in this sense, we have followed a very, I would say, systematic approach, depending on the level of supersymmetry that we preserve. So already for more than 8 supercharges, it was proven by Cecotti years ago that it was always true, because the modular spaces are always coset spaces. And then you can use this to prove that the BP states will always decay exponentially. But with 8 supercharges, the story is less trivial, it's much more complicated. And the past few years, there has been a lot of work, like trying to understand identifying exactly what are the towers that become light at all possible infinite distance limits that you have in Calabi-Yau compactifications of string theory or F theory. So maybe I'm gonna skip this because maybe it's a bit too much. Let me just say the way to proceed is that we identify that there is always some monodromy transformation around the singularities, which is some discrete symmetries and discrete axionic symmetry, which has to be of infinite order in order to be at infinite distance, and this populates the infinite tower of states. So it seems that there is a deep connection between these towers of states and the discrete symmetries that appear in the different limits. And let me just give you what are the lessons that we have learned from all these studies in string theory. So first of all, I think one of the cool things is that by checking the distance conjecture, we have learned new things about the string theory compactifications and the underlying mathematical structures of the Calabi-Yau. So this has allowed to have systematic classification of the singularities that was not done before. And also the advantage of testing these things in the string theory is that we can be very precise and we can compute all these order 1 factors that are typically unknown. And for example, in all these examples, I mean, we can give a bound, a lower bound for this alpha, which is related also to this discrete symmetry that I was talking about. Okay, so these monodromies characterize the different types of limits and also tells you what is the exponential rate. and these integers are bounded. Okay, they cannot be bigger than the dimension of the space. So in particular, for a Calabi of 3, 4, you can only have 3 possible options for the exponential rate of the tower, which is 1, 2, and 3, and that's it. Now, we have also learned that it could be just a matter of these setups with 8 supercharges, but all these infinite distance limits are always weak coupling limits, in the sense that you also have some p-form gauge coupling that vanishes asymptotically. So you have the discrete symmetry, but you also have these p-form gauge symmetries. And then the distance conjecture tower, I mean the tower of the distance conjecture, is also satisfying the weak gravity. So all the evidence that I'm showing you here is not only for the distance conjecture, but also for the weak gravity conjecture. Okay, because all this stuff, I mean, you can check that the tower satisfies the weak gravity. And this might be more trivial if we are talking about BP states, but it's non-trivial when we are talking about non-BP states that have also been studied in these setups. So, and in those cases, yeah, then the exponential rate of the tower, which is like an order 1, like the open, an undetermined factor in the conjecture, is fixed also by the extremality bound of the black holes. Okay, because the same tower satisfies the weak gravity and the distance conjecture. So I think that in all these examples, I don't know, it's just, there is just one statement that works, like you get this tower of states and they have these properties which satisfy both conjectures at the same time. And probably in the future, we will just unify the conjectures, I think. Okay, and also just as a comment, so far, all the towers of states that we find are made of particles or string modes. And this is what led Timo Weigan and collaborators discuss this emergent string conjecture, in which they claim that this is the only thing possible. But this is just based on examples. So it's an open question whether this tower of states could be made of something which is not a particle or a string, like a membrane or a higher dimensional object, which would be very interesting, but also extremely surprising, because that would mean that we get some sort of membrane theory in lower dimensions or something like this, which is weakly coupled. And it has been a very difficult thing to find a membrane theory already. I mean, like a weakly coupled membrane description for M theory. So it would be amazing if we can find it. Okay. Any question about this? Okay, so all I told you was about flat space. There are also recent developments on ADS-CFT, in which the question gets translated to what happens if you move in the conformal manifold of the CFT of marginal couplings, right? And so these marginal couplings are going to be mapped to the massless scalars in the bulk. And the question is whether we can find, maybe we can use ADS-CFT to find some reasoning or try to prove the conjecture, no, in a more general sense and not just by checking examples. And here, what we found is that it seems that at every infinite distance limit in the conformal manifold, the tower is always a higher spin tower. It's always made of higher spin fields. Okay, so what we did is to connect these three notions of infinite distance measured by the samological metric, having a free point in your theory in which a gauge coupling goes to 0, and having a higher spin tower. And I put here in green the directions of the arrows that are proven, at least in the context of superconformal field theories, versus the one that is just based on examples but has not been proven in general. Okay, so the relation between free points and higher spin tower, I mean, this is proven by Malazena-Sigvoedov, but we also prove that in superconformal field theories, this free point is associated to a gauge coupling that goes to 0. And then we can prove that this is going to be at infinite distance, always by measured by the samological metric. And the part that is non-trivial is that this is the only way to go to infinite distance. Okay, so that infinite distance necessarily implies to have these free points in which some sector of the theory decouples. And it's related to the fact that this is the only way we know in which conformal perturbation theory breaks down. So that's it really costs you an infinite distance to reach that point. But okay, I mean, I can say more things, but maybe this is just the underlying message. When I say that the green parts, the green arrows are proven, is because if we are in a near some free point, not that the gauge coupling is small, we can just use perturbation theory to compute what would be the metric exactly, right? Because then the marginal operator is just going to be trace of f squared, and then the metric has this hyperbolic form. So it's going to be at infinite distance, and then the anomalous dimension of the higher spin operator that tells you how much we deviate from the unitarity bound is going to decay exponentially in terms of the distance. So this is the equivalent statement of the distance conjecture, that now we get an infinite tower of operators such that the anomalous dimension of these operators decays exponentially in the distance measured by the Samologikov metric. Okay. And one of the nice results is that here we can compute exactly again what is this exponential rate. And when we translate it to Planck units, it's lower bounded. So in particular, the result for the exponential rate of the tower is 2 times the central charge of the theory times the dimension of the gauge group that gets free, which means that this has a lower bound because the central charge has to be bigger, right? So that this dimension of the gauge group. And this is good because a lower bound on alpha means an upper bound on the field range. So it goes in the direction that you cannot travel parametrically far away. Okay. Okay. So also this work is beyond Einstein gravity, so it also hints that the distance conjecture could be something more general than having a weakly coupled Einstein gravity theory. Now, maybe, what time is it? Okay. I wanted to say a last few things about the distance conjecture, and then I just have a couple, 3 slides about the potentials. So I wanted to say a few words about what happens with the distance conjecture when we have a scalar potential, because all the phenomenological implications depend on whether this conjecture applies when you have a scalar potential in your theory, right? If you want to use it for inflation and so on. And the evidence that I showed you before, it's actually about flat moduli, like exact moduli spaces. Okay. So it's very important. I think most of the work this year on the distance conjecture is precisely going into understanding what happens when you have the scalar potential. Okay, so in principle, already in the original paper, the idea is that this conjecture should apply even if you have a scalar potential, because as long as the energy scale is small compared to the cutoff, so that the potential is not obstructing to go to the infinite distance, like when you have these runaways behaviors and so on, so that within the effective field theory, you can still reach some infinite distance limit. If that's possible, in principle, the conjecture should apply, because otherwise we get the same problem that with the weak gravity. It seems that, imagine that we are at a very high energy scale, everything looks flat, everything looks massless, the distance conjecture is satisfied, but now we look at it at a different energy scale, and then the conjecture is not satisfied. So, it's weird. The only way in which the conjecture could be consistent at any energy scale, and that quantum gravity doesn't care about what energy scale you are looking, is that the values of the potential should also obey the distance conjecture, which in turn...
Can you just say again, what was the Swampland distance conjecture at an energy scale? How is the distance conjecture know about an energy scale?
Imagine that, so the distance conjecture is about geodesics, right? But the notion of geodesic changes depending on the energy scale. That's the problem. Because if you are very high in energies, from a physics perspective, if you are at a very high energy, even if you have some small potential, this looks like flat. And then the geodesics are just I mean, you can just compute the geodesics of that full moduli space. But if you now go to lower energies, you get sensitive to the potential. And then if you look at the effective field theory below a certain energy cutoff, you get a new moduli space, which might be different from the one above because you can integrate out some fields, no? So you lift some directions. And then the geodesics in this new moduli space could be different from the geodesics that you have originally. So it could be that originally you were satisfying the distance conjecture along some UV geodesics, but then you do not satisfy along the IR geodesics unless the possible potentials that you can have in your theory are constrained. So that the values of the potential cannot be, like I put here, like these highly turning trajectories should not be allowed because otherwise, from the low energy perspective, this value of the potential, like if it's really like you have some hierarchy, no? So you really have like some one-dimensional moduli space in the infrared, which is like a spiral. This spiral, if it can be parametrically large, would be violating the distance conjecture. If you can make this spiral as large as always. So the distance conjecture itself is not just constraining the field metric, but it's also constraining the scalar potentials in quantum gravity. That's the idea.
Is there a more invariant way to say it? I mean, what I liked about the previous conjectures is that you said something about symmetries or about masses of particles, things that are directly observable. The potential I don't think of as usually a very directly observable thing. I think it could change under dualities. I think so it's just something in the Lagrangian. What is the observable part?
Well, but that's why whether the distance conjecture is satisfied or not should not depend on that scalar potential, precisely because of what you said. So the idea is that if in your effective field theory you can engineer some infinite distance limits, doesn't matter how, that should be abstracted, because we believe that there is some global symmetry or something that gets restored in that limit. And that implies that there is no way to fool yourself with having some scalar potential that allows you to have a very highly turning trajectory and therefore have a parametrically large variation that would violate the distance conjecture, because that's something that you do in your effective description, but quantum gravity shouldn't care about that. It should only care about how close you are getting to restore that global symmetry, like how large is that field variation. Doesn't matter how you engineer that. And that's my understanding of this. Of course, then one has to check it. I mean, and of course, like whether it's true, because it's highly non-trivial that then the distance conjecture is satisfied, because then, as I said, like you are also constraining the scalar potential that you get from string compactification and so on.
By the distance conjecture, you meant the exponential
I mean,
tower?
exactly, the exponential tower. I mean, the exponential tower. So how the exponential towers relate to the field distance that you travel depending on the scalar potentials, right? So like the exponential tower depends on some distance, and that distance depends on what is the value, no, of the potential, what is what trajectories you can follow.
So it's a constraint on the allowed scalar manifold, basically, is what you're saying.
Yeah, it's a constraint on the allowed scalar manifold. Yes.
Okay.
Yeah, all I wanted to remark is that a constraint on the scalar manifold is not just a constraint on the metric, the kinetic term, but also on the scalar potential or whatever.
But a low energy person will just solve for the minima of the potential and just call the result the new scalar manifold.
Yes, exactly. Yeah, that's what I mean. Yeah, that's what I meant with at any energy scale. Like you have a new effective field theory, and that's your new scalar manifold, and you should get an infinite tower of states also there.
I see.
But requiring this to happen is, like it imposes non-trivial constraints from an effective field theory perspective on what scalar potentials you can use for inflation, for example.
Yeah, you're not talking about exactly flat directions. You're talking about trajectories at some finite energy. So it's not really, it's not so straightforward, I think.
Oh, okay. Then I don't get it.
It cannot be flight directions, right? Because mass depends on it.
Yeah, that's why I put here pseudo moduli spaces.
By definition.
But they're masses of some things that you weren't caring about before, though, in your effective field theory.
But I thought the
They
point
come-
is the things come
Yeah,
down.
they eventually come down, and the
Yeah,
effective field
so
theory
these
breaks
cannot
down.
be really flight directions. So, you know.
Yeah, that's the point. It's not just about flat directions, because the notion of flat, I mean, like from a physics perspective, right? If something is super, super small comparing to the energy that you are proving, it looks like flat. Like there should be a continuous way in which the distance conjecture, the exponential tower appears. Like there is no drastic thing. Suddenly you get an infinite tower. So the idea, is that it applies to whatever looks flat from your energy scale, from the cutoff of that theory, but it could still have some small mass, right? It's just that it's very small comparing to the cutoff. So that's why it applies. That's why, in principle, the distance conjecture applies to inflation, because you have some, right, like some slowly rolling down potential. So it's like a nearly flat trajectory, but it's not exactly flat. But still, if this trajectory allows you to reach some infinite distance point, because the potential is decreasing, so it's more flat, it's more and more flat, then if the tower is linked to the infinite distance limit, doesn't matter that you approach it exactly flat or not exactly flat. Like if there is something wrong with getting too close to that limit, you should also get sensitive to that new physics and that tower, even if you have a small mass.
Can you say the constraint on without using the word potential?
Constraints on the level of on the geodesics, but that depends on the scalar potential as well. If you wish, like you take some effective field theory, that you have some cutoff, and you study the scalar manifold for the scalars below that cutoff, no, with masses below that cutoff, and you study geodesics in that scalar manifold, and then you should get the infinite tower of states decreasing in terms of the geodesic distance. The thing is that this notion of geodesic depends on what is the cutoff that they put, because then you integrate out some scalars or not, right? Like the scalar manifold changes. So it constrains the level of non-geodesicity, if you wish, from a UV perspective that the geodesics in the IR can have. Is it clear?
No, but you should keep going.
How many conjectures are we still going to go through?
No, I just have 5 more slides about the last 2 of the potential.
Okay.
Yeah, let me finish and then we can ask.
Perhaps you should just go to the.
Yeah.
Just go through then.
Yeah, let's just go through. So just wanted to say that this is something that, we are working on testing, like studying the potentials and the geodesics and so on. And so far, we have proven that this is the case in the Calabi-Yau compactifications, that the values of the potential deviate from geodesics of the UV just enough to allow to have still the exponential behavior of the tower. So it's something that is example-based right now, but will be interesting to check more generally beyond the Calabi-Yau compactifications. Okay, let me skip this. So the last thing, just to finish the review, is to say a few words about these recent conjectures about the potential, just to clarify exactly, I think, what is really known versus postulated, as you asked for. So let me say a few things about the de Sitter. So it was proposed by Kumron and collaborators that the scalar potential of a quantum gravity theory should satisfy this constraint on the slope of the potential, which was then forbidding the existence of the Sitter vacuum and so on. And then there are different refinements in the sense that this should only be satisfied if this condition on the second derivative holds, or that this only needs to be satisfied if you are near some of these boundaries of the field space. And otherwise, what happens is that the de Sitter, you can have a de Sitter vacuum, but it has to be short-lived. Okay, so here there is like different proposals and so on. And I think, at least in my opinion, the evidence that we have for this only comes from the behavior of the scalar potential in string compactifications near these boundaries of the moduli space. Okay, so it's true that near the infinite distance limits, when we approach the boundaries and we get these exponential, these towers of states, there were already many no-go theorems for the Sitter vacua in the literature. And also recently we have generalized these no-goes beyond weak coupling, so that in general, when you approach some infinite distance limit, you always get this runaway behavior of the scalar potential. So I think when studying this conjecture, it's important to keep this in mind, that it's a very important question to understand whether there is the Sitter is allowed in quantum gravity or not. But at the moment, I think the solid evidence that we have only applies when we are near the infinite distance boundaries of the field space, which doesn't mean that you cannot have a de Sitter vacua deep in the bulk of the field space. Although this could come with the problems that you are not near some region of perturbative control, and maybe you are not even near Einstein gravity. So it would be very nice to try to quantify how far you can deviate and you can go from these boundaries so that you still have some Einstein gravity, because in the end we need that our universe is weakly coupled, right, somehow, but still maybe try to evade these no-go theorems. And that's why I call it asymptotic de Sitter conjecture, okay, because it's only about asymptotic limits. And yeah, just one of the reasons why this could be true is precisely because the tower of a state that becomes light when we go to the boundaries is responsible for generating this runaway behavior of the scalar potential. Okay, so it's not just that we get new light states when we approach the boundaries and try to engineer global symmetries, but also that these new towers of states constrain the effective field theory that we can have, because the scalar potential will receive corrections, right? Like you have to integrate out this tower, and the corrections from integrating out this tower will induce this runaway behavior. Okay, so this is it for the de Sitter conjecture, and let me just say a few words about this one, and I finish. So the other one is the non-supersymmetric vacua, non-SUSY-ADS conjecture, claiming that any non-supersymmetric vacuum should be metastable, so that it should eventually decay, so that there is no way to guarantee stability unless you have some supersymmetry. Okay, here the motivation came from the weak gravity conjecture, because indeed, if the weak gravity conjecture holds and you have some vacuum which is supported by fluxes, so that you have some gauge fields living on the extra dimensions, and this gives rise to some fluxes in the vacuum, then you need to have some brane that is charged under the fluxes and has some tension smaller or equal than the charge. And then Hirose and Kubrun argue that if you don't have supersymmetry, then the tension is going to be strictly smaller than the charge, because there is nothing that protects the tension from getting corrections and deviating from the exact equality, and this automatically implies some bubble instability of the vacuum.
Aren't there counterexamples to this?
There are no, so there are counterexamples.
The Perlmutter Giambi double trace deformation.
Yes, but that's about breaking supersymmetry with the boundary conditions, right?
What's the difference? It's a non-supersymmetric CFT with an ADS dual that's manifestly under control.
It's different because the idea here is that this motivation from the weak gravity applies, like if you have some.
Yeah, but you have it in a parenthesis. Non-SUSY CFTs cannot have ADS Einstein gravity dual. Isn't this being falsified by this example?
Okay, maybe. Yeah,
I mean, I'm not sure how to invariantly characterize those examples for which this mechanism is important. Not everything is just a stack of brains.
Yeah, so when I say non-SUSY, it's true. I should be more careful about that. The point is that you have to break supersymmetry like in the bulk, right? It's not just a matter of
the
boundary
actual
condition.
CFT doesn't know that at all, right?
Yeah, no, it's true that from the CFT perspective, that should be pointed out. That's true. I agree with that.
Well, we should somehow know, shouldn't it? Like high energy states should be approximate, like the high energy spectrum should be approximately supersymmetric. Or what does that mean? I guess.
Yeah, no, maybe that's right. Maybe there's approximate equal degeneracies of trace minus 1 to the f at high energies.
Yeah.
No, I mean that's people study broken supersymmetry all the time in phenomenology. So I'm sure Lian Tao can tell us exactly what to look for. But
no, I thought that this is like you're talking about really in order to access to the bulk, you're really talking about really high energy states, right?
Yeah. Well, I think this example Clay is talking about is supersymmetric in the bulk, largely, right? And then you just
it's like
you'll probably have some degeneracy.
Yeah.
There's something special about it. I mean, it doesn't change the fact that this statement is not precise enough to distinguish. Indeed. So
I'm just complaining that I think that as written, some of the statements here are not correct.
It would be amazing if something like this is true. I mean,
it will be amazing. Any of this is true.
Well, I mean, I think here, yeah, it's true. One has to point out that it's important you're breaking supersymmetry in the bulk. It's not just a matter of boundary conditions. And it's an interesting question to understand how to distinguish that from the perspective of the CFT. But if there is a way to distinguish, I mean, it's just a matter of definition, right? Like how do you distinguish that? And the point is that, okay, if there's a way to distinguish that you are really breaking supersymmetry in the bulk, then that's, you should not have, right, a CFT, I mean, the boundary, right, it's going to be ill-defined. So there's non-SUSY CFTs that you cannot have. If you have a non-SUSY CFT, either it's an ADS Einstein gravity dual, but it's done with this trick that you are just breaking supersymmetry with boundary conditions, or it doesn't have an ADS Einstein gravity dual. And I agree, it would be amazing to understand better from the CFT perspective why there is this correlation between Einstein gravity and supersymmetry.
well, there could be some very neat deep condition on CFTs that could have could be the holographic rules.
But you have to say the word Einstein very loudly when you're saying this, right? Like Vasiliev is, like it's somehow the gap to higher spin particles must be essential.
Yeah. Okay. Yeah. Good. Yeah. Should have Einstein grabbing picture and something. Yeah. Yeah. Otherwise, everything. I mean.
Yeah. Otherwise, almost tautologically, there's counterexamples.
Yeah. It's about Einstein gravity, which is also related to the absence of global symmetries. Like, I mean, we need to quantify this much better, right? But all these things I'm talking about, it works when you have gravity dynamical and you have some Einstein gravity. It doesn't work, for example, if you are in 2 dimensions, right? And like a Worldsheet theory has global symmetry. So this is something that, of course, has to be characterized much better. But it seems that like all these conjectures are telling you that there is something different there. And it's a matter of defining this better. Okay, so let me go to the last slide. So because I guess this is taking too long for you. So the last thing I wanted to say is that regardless of this with gravity conjecture, even if we don't have gauge fluxes, we could also try to prove this conjecture from the bulk perspective in general by showing that we always have bubble of nothing instabilities. So the point is that if we have internal dimensions, we could have this Witten bubble of nothing, right, in which we nucleate a bubble with nothing inside. And whether this is possible depends on whether the internal dimensions that you have can be shrink to a point. Okay, because what happens is that, for example, in the case of Witten, you have a circle that is shrink to a point at the boundary of the bubble of nothing. And the interesting thing is that whether this can be shrink to a point is equivalent to ask whether your manifold is the boundary of a manifold of 1 dimension more, which was the same question that we discussed with the coordination group. So if it's true that there is no topology, that the coordination group is trivial or within quantum gravity, it would mean that you can always construct at the topological level some bubble of nothing instability. And we actually use this in particular examples in which we can really show that the coordination group is zero to construct new bubbles of nothing that generalize Witten's construction, so that instead of a circle, we can also have like a 3 torus with periodic boundary conditions, so that you have some supersymmetry at high energies, but still the vacuum breaks supersymmetry, and there is no topological obstruction to generate the bubble of nothing, and we construct the solution to the Einstein equation of motion to show that indeed you get an instability. So I think here there are many more things to study, and in particular, in order to make this, to transform this into a proof, one also has to show that the energy conditions that you need to violate in order to be energetically favorable to expand, to decay, so that the bubble will expand, are always violated when you break supersymmetry. Okay, so they are typically violated. This is like the dominant energy condition and so on, but it's not proven if they are sufficient. And it's also interesting that these energy conditions, when you have fluxes and gauge fields, they get modified to something that looks again like the weak gravity conjecture. So I think everything just, I don't know, in the end, it's just about understanding what are these topological obstructions, which is associated to global symmetries, and understanding precisely what topological, I mean, whether any topological operator should be forbidden in quantum gravity or not, and also understanding these energy conditions in more detail and what is the interplay in quantum gravity. So
in the supersymmetric case, what stabilizes the, I mean, it's just, is it fermion zero modes or something that they stabilize the known cases that are stable?
So what happens is that in the supersymmetric case, you are satisfying these energy conditions. So it's just a matter of energetics, which means that if you try to compute the Euclidean action for the solution, is going to diverge. Yeah. So the decay rate goes to 0.
Gotcha.
That's what happens. So it's it's about this energy condition.
Exact balance, so you can make the bubble, but it won't grow.
Yeah. Yeah. So you need Susie Bogan for that.
Yeah.
Yeah. So some work now is going precisely to understanding these energy conditions in more detail, and the interplay with supersymmetry, and what is the interplay also with the other conjectures. And this is what brings another connection of this map that I showed you at the beginning. Okay, so I think this is it. Let me, there is the distance conjecture, but we can just ignore it. And just let me conclude. So yeah, so I think the message is that consistency with quantum gravity have the potential to have phenomenological implications. And it all comes from understanding better what is the quantum gravity imprint at low energies, which is a very ambitious goal. And that's why there are many things which are just conjecture and are not clear yet. But one thing which is clear is that all these conjectures are starting to get related. And I really hope that they will get reduced to a very few number of statements in a few years. I mean, we have gathered more evidence in certain setups and corners in support of some of these conjectures. And sometimes I have to say that working on this from the context of string theory compactifications, it's, I don't know, sometimes it's highly surprising how string theory managed to satisfy the conjecture. Like, it's really non-trivial for these exponential towers and so on, how they always get down and you always get infinite tower and so on. So I think there is something behind, which doesn't mean that every statement will survive. I mean, the whole goal here is try to prove or disprove what it is and try to make it precise, and understanding what are the underlying principles behind it. So there is much more work to do. And I hope you enjoy the talk. So thank you very much.
All right, great. Thank you very much. I figure we should probably take a break, but if there are any other quick questions.
I've asked my quota.
I mean, I think we should thank you. We gave you a very difficult task.
Thank you very much.
Yeah, let's thank the speaker
it's okay.
again.
The more questions, the better. I mean, we are here to learn. So